Okay, we're back here for the last torque practice problem from practice 2. This is number 3B, where we're looking at the horse with the rod, but this time we're just concerning ourselves with the rod, and we want to figure out how much torque the rod is applying to itself due to its own weight. So the first thing to recognize is that this is the pivot down here for the rod. That's what it's rotating about, so that's our pivot P. And the hint we have for this problem when thinking about the rod is that we need to use the center of mass or the center of gravity. Now, when we take a look at this rod, it is a completely uniform rod. It's not, a weird mass distribution. It's not shaped funny. It's just perfectly uniform, which means the center of mass or the center of gravity is directly in the middle of it, which means that if the entire thing had a length of 3.6 meters, this force due to its weight, and remember weight always acts directly down, this is the weight of the rod, which is 2,500 newtons in the problem. This means if we're halfway here, we're halfway at the 3.6, which means our moment arm, which runs from the pivot to where the force vector is applied, that R value has a value of 1.8 meters. It's just half of the 3.6. So we've got an R, we've got a force, the weight going on, and that means when we take a look at torque, torque equals R cross F, or RF sine of theta. We need to figure out what this angle is in the problem. We have this angle here of 70, but looking at this, that 70 doesn't really belong into anything we want. Let's just follow a tried and true method of redrawing the pivot, redrawing the moment arm, and then let's move that force vector back to the pivot and see what happens. Well, if we move this downward force vector, the weight, back to the pivot and draw it down, here's our force, the weight, here's the moment arm up here. We want the angle from the moment arm, R cross F. So R to F, that's the angle we want. The only thing we have in this problem is from the horizontal, this angle here is 70 degrees, and just with a little bit of geometry, we can note that this is 90 right there, which makes the entire thing 90 plus 70, or that the angle we're looking for is 160 degrees. We can just shove that back up there. This allows us to quickly solve for the torque. Our R is 1.8, the force is 2,500 newtons, and then we have the sine of 160 degrees. Quick little calculator, 1.8 times 2,500 times the sine of 160 gives us 1,539. So 1,539 newtons for the force, meters for the distance. And that's our torque. If we want to figure out the direction, if we imagine that we snipped the rope here, we cut it, this rod would start to fall this way, right? Well, looping around like that, we can see that this is a clockwise rotation, which is negative in the world of mathematics. And if we take our fingers and we kind of make a chicken wing or bend our arm, or maybe we're doing this on paper, we see that our thumb, when we rotate our fingers in the direction of the rotating rod, our thumb's pointing into the screen, or maybe it's pointing into our paper, so we can say that our torque here is in as well. So our three directions are into the page or the screen, negative, and clockwise. And that's it. That's the last torque problem. Hopefully that worked out well for you. A little bit of geometry here and a little bit of right hand rule trying to figure that out, but nothing too crazy. So take it easy.